to you guys about diodes today and LEDs. Alright, so who here has a diode or LED in their project? Nope, you don't have diodes in your project? No? Alright, who here doesn't have a diode or LED in their project? Have you guys looked up what they do? So what do they do?
So I had to use them for my starter project, and basically I think a diode allows the current to flow in one direction.
Right. Alright, so I'm gonna kind of explain how it does that. So first of all, do you guys kind of know the difference between insulators and metals, or conductors, I mean? So why do insulators insulate electricity, and why do metals conduct electricity? Yes?
Because the composition of a metal has electron seas, and that pretty much means like the electrons are free flowing.
Right.
So it's easy for like electricity to flow through them.
Right, so if I had so let's talk about insulators first. Right, so if I had an insulating material, and these are the nuclei of the atoms in the structure, does anybody know what happens to the electrons and what type of bonds they form? Anybody? Yes. Covalent? Yeah. So what they kind of look like this, right? They kind of just all connect in a lattice. You guys get the point, right? They kind of all connect like that. And what does that mean about the electrons? What does that mean for the electrons? Yes.
They're shared.
They're shared, but what else? Like in terms of electrical conductivity?
It's not easy for them to give up electrons, you mean?
Yeah, kind of. So when you have covalent bonds, the electrons in between the atoms, they're bonded between each other, and they're not free to flow, which is why they don't conduct electricity. In metals, however, you have, like Hadassah said, you have your sea of electrons, and what that means is so what that means is, what happens? So you have electrons floating in between the spaces of the nuclei. So obviously the nuclei, most of you guys should know that they're positively charged, right? So the electrons are there to keep everything bonded together, so they don't fall apart, so they don't crumble like sand. But they're also free to flow. So if I put a voltage across the two ends of the material, the electrons will move towards the positive side. And yes.
So what causes metals to have the sea of electrons and not other materials?
That I cannot explain to you off the top of my head, but I think it's to do with, so if you look over here, it's to do with their atomic structure and how many electrons they have in terms of in their outer shell, so their valence electrons. I know I'm saying things that not all you guys will understand, but it just means sometimes the electrons are held really closely to the
so it's
atom.
size-wise?
Kind of, yeah, kind of.
Like the ionic radius?
Yeah, kind of like that. But, yeah. That's a good question, though. But otherwise, that's how metals or conductors and insulators are different. So, does anybody know what a semiconductor is? Someone else. Sorry. Razan's voting on. Yeah, Alec.
It's the conductivity between a conductor and an insulator, so it's not as conductive as a conductor.
Right. Okay. So who can name the most common example of a semiconductor? Yes.
Silicon.
Silicon? Alright, so silicon I've drawn up here it's Si, and it has an atomic number 14, which means it has 14 protons and 14 electrons. And I actually have it drawn up there. So as you can see, you have your center electrons, kind of, and then you have 4 outer electrons. So what those 4 outer electrons can do is they form bonds with their neighboring atoms, and they do things. So who knows about the conductivity of semiconductors? Yeah.
It's like current on and off.
Kind of. So if I just had an array of silicon atoms right here, and I told you that each of them has 4 outer electrons. So when they form bonds with their neighboring silicon, they kind of form bonds in this manner. So obviously I'm drawing it in a 2D plane. They actually form, pretty sure they form tetrahedrals. So that means this is actually 3D, and it's not just flat. But you get the point. So silicon, they bond ink. So they don't have metal bonding, right? But we also know that they conduct electricity, right? So does anybody know how that happens? So okay, actually first, do you think silicon conducts electricity in this configuration? Right? Because it doesn't have any free electrons to move through, right? So the way you make silicon conduct electricity is, so you have to dope it. And it's kind of a funny word, dope, but what it means is to introduce impurities into the silicon crystal. And there are a couple of different ways of doing that, but essentially what they're effectively doing is swapping out one atom for a different atom every once in a while. And what that does is, for example, if I wanted to turn it into a material that has positive charges, I would dope it with arsenic, which has 5 outer electrons, right? So if I put arsenic over here, it has an extra electron, right? Or positive proton. So it's a positive charge, right? So now, if I do this every once in a while, I can create a material that has charge. And so actually, sorry, I'm mistaken. So arsenic has 3 outer electrons. And what happens is it only bonds to 3 things, and there's an empty space for an electron to fill. So when you apply electricity from, like, say, a battery, the electrons from the battery will come through your silicon and your doped silicon, and the charge can flow because you have holes for it to fall into. So what happens is you get an electron that comes through here, and for example, this was another arsenic atom. So you have another hole over here. So what it does is it jumps into this bit, and it forms a bond, and then it jumps into this bit, forms a bond, but then it jumps into that bit, and so on and so forth. Right? So that's how you get charge to flow. And you can do the same thing by swapping it out for an atom that has 5 electrons, 5 outer electrons, like gallium. And what will happen is with 4 of its electrons, it'll form a bond, form 4 bonds, and it'll have an extra electron. And then when you apply voltage through it, it kind of behaves like a metal. The electron can flow wherever it wants because you have a bunch of places for it to go, and you also have free electrons. So that's kind of how that works. All right. So when you have an extra electron, it's called a p-type semiconductor. If you dope it with a different dopant that has 3 electrons, it's a p-type semiconductor. So it's an electron acceptor. So P-type things are acceptors and N-type things are donors. Not things, but semiconductors. So the way people make diodes is this. The way people make diodes is they get a piece of silicon, crystal of silicon, right? And they split it, but they don't actually split it down the middle, but they kind of split it down the middle by doping one half of it positive. So I got my P-type silicon over here. And then I got my N-type silicon over here. And this setup will only let current flow one way. And the way that works is if we look over here. So let's say, for example, can anybody tell me whether this is the positive side or a negative side?
Negative.
Negative? Right, so I got my electrons over here. Right? So I'm going to show you an example of hooking up a diode the wrong way to show you why it doesn't work. And later on we can talk about a diode that's hooked up the right way in forward bias. So this is in reverse bias. It means you hooked it up the opposite way that was designed for it. So, I put a battery, so I put the positive terminal of the battery to the negative side and the negative terminal of the battery to the positive side. Can anybody tell me what happens to different opposite charges? They track. Right. So if I put positive charge, or if I give this side positive potential and this side negative potential, can anybody tell me what happens to the charges that are formed? What happens to holes in electrons? Yeah.
Doesn't it become neutral?
No. So if I have a big positive charge over here, and I have a big negative charge over here, what happens?
Like, all the negatives are going to go like outside the diode,
Right.
And all the positives are going to go outside,
Right.
And then nothing's going to happen.
Exactly. So what happens is they separate out like that, right? So you get a bunch of negative charges all over here, and then you get all your positive charges all over here. Yeah? And then in the middle, what you're left with is just normal silicon. So right here, you only get normal silicon. So it's not doped N-type anymore, it's not doped P-type anymore. So does anybody remember what I just said about silicon by itself in terms of electrical conductivity?
It doesn't conduct
It
very
doesn't.
well.
It doesn't conduct very well, right? So what happens here in terms of current?
It can pass through the middle.
Right, so it doesn't flow anymore, right? So it stops current from going this way into the diode. Yeah? So what happens if I hook it up this way? So you guys said I have all my positive charges right here. I got my negative charges over here. Can anybody guess what happens?
Charges will go to the middle of the diode because they're opposed side out.
Right, exactly. So the positive charges are forced this way. Not only because, well, actually, yeah. So you get a big positive charge over here and a big negative charge over here, right? First, the positive charges are repelled by the positive end of the battery, and they start moving forward. And once they're in this area, they start getting attracted by the negative terminal of the battery, so they got pulled through, and they kind of cycle around. And the same thing happens with the negative charges. They come this way by the same logic. So in this configuration, you have a diode that's current flow, right? So when you hook it up the right way in your circuit, it lets current flow. And if you don't, then it doesn't, obviously. Okay. So does anybody know what LED stands for? Somebody in the back want to answer? Eduardo, what does LED stand for?
I didn't read my hand.
Huh?
I didn't read my hand.
Yeah, but I'm asking you.
Light emitting device? I don't know.
Close. You got light emitting, right? John, is it? Yeah.
Like emitting diode.
Right.
Oh.
So it's light emitting diode. What it means is this thing is basically like a diode, and it's definitely built from a diode, and the circuit symbol for it is a diode with arrows for light coming off of it. It's kind of stupid, but that's what they came up with for that. So the reason some diodes can emit energy is so everybody knows that this is a atomic structure of an atom, and you see how these things have different orbitals, right? So these electrons have different levels of energy they can be at for it to, I don't know, do stuff. Obviously, silicon only has 14 electrons, so that's all of them. But if you give it enough energy, these electrons can jump to the next orbital and have this be just empty. It can jump to the next orbital. So you have discrete energy levels. What that means is you either have it excited or you have it not excited, because they can't exist in the middle, right? They can only exist in orbitals. So you have the baseline energy and super excited energy. So, and I have my electron over here. So when you guys pass current across the LED or through the LED, what happens is you're giving these silicon or semiconductor atoms energy, and what happens is they jump to the high excited state, right? Does anybody know what happens, like, what do people say about energy, like that it can't be
Lost.
right or destroyed, right? There's energy in the universe is conserved, right? So I gave it energy for my battery, but once that electron's done being excited, it wants to come down. So where do you guys think that extra energy goes? Yes.
Creates a photon.
Right. So when it jumps down, when it comes back down, it's got all this excess energy that it doesn't really know what to do with. So it shoots off a photon. And that's how you get an LED source. So that's what happens inside your tiny little LED, is that these atoms are constantly getting excited, and they also come down from excited state, and all the excess energy is emitted in the form of photons. Who's using Rgb LED in their product before? Oh, you guys, I know you got an Rgb LED, right? So, as you guys probably figured out, there are two different types of Rgb LEDs. You have common anode and common cathode. So, Rgb. So I drew them here. So yeah, I guess I'm trying to point out the fact that you hook these two things up differently, and you apply power to different ends of the LED, and you have to ground the other side, depending on what type of RGB LED you have. Right. So can anybody tell me where I would hook up power and where I would hook up ground on this one? Anybody? Eliana, where do I put ground on this? You're not sure? Oh, you should be sure, because it's in your project, right? Alec, where did I put ground?
At the top?
Right. It's at the top. So I put ground over here, and I apply, what, 3 volts, 5 volts down here. What happens if I try to put 5 volts through the top and ground at the bottom? Yeah.
Same thing you explained over there.
Right.
Ground voltage.
Yeah, so the dopants in the silicon, they separate out, and they form a barrier known as depletion zone. You guys probably won't have to hear this word again until college, but the bit in the middle is called the depletion zone. And the reason it's called the depletion zone is because the silicon or the semiconductor is depleted of its charge carriers, so it can no longer carry electricity, and therefore current doesn't flow. So when you don't get current flowing through the LED, you don't get this electron excitation and opposite of that. I don't know what that is. So you don't get this happening, and that's why your LEDs don't light up when you hook up like that. Yes?
So if the light is being let out, like if the energy is being let out through light, what happens in the diodes? Where does the energy go there? It just goes through?
Right, so over here you have charges flowing in opposite ways, right?
But the LED doesn't have that?
No, the LED has that.
So,
But on top of that, so this is just a diode, but what happens over here in the charges is they're not, when I say they get excited and they get to a higher energy state, they don't literally, like, in terms of like the 3D universe, they don't move anywhere, they kind of maybe vibrate a little more, but they have more energy and all that. So they still move like that, but as they're moving, they can move with more energy or less energy. Does that kind of make sense?
yeah, so, but does that just get less energy in the first place, so it doesn't have to emit some of it?
Right, so before you put a voltage across it, it's just sitting in its regular state, right? So if you just had a piece of silicon, as if you just had like a piece of any type of material, and you just have it sitting there and you're not doing anything to it, it has a certain amount of energy, right? Because you guys know about absolute zero, right? So it's the point in terms of energy and temperature and all those things that are associated with temperature or energy. I mean, it means it has absolutely no energy. So obviously it has a temperature, right? It's room temperature. It's what, like about 300 degrees Kelvin, which is like room temperature. So it has energy. So it's not absolute zero. It has a little bit of energy. But that energy, what that's doing is it's keeping this atom intact, and it's keeping it from collapsing on itself, and it's keeping it from like throwing all of its electrons out. So that's what that energy is doing, and it doesn't have any extra energy to spare to do any work, right? It's using all of its energy so it doesn't implode or explode each atom. And when you put a voltage across it, you're giving it potential energy, electrical potential energy. So the electrons, or even the holes or the positive charges, they can become excited, and they can, after they get excited, they come back to their ground state, and the extra energy that they had before, now that they want to get rid of it, becomes a photon.
Wait, but I don't understand why normal diodes don't do that.
Oh, so that depends on how diodes are made. So remember how I said, so for positive charges, I say arsenic, and for negative charges, I said gallium. So when you're doping the silicon, you're doping it with different types of materials for it to do different types of things. There are many things you can dope it with. It's not just arsenic or gallium. You can dope it with. You can dope it with like phosphorus. You can dope it with like germanium's a base. You can dope it with any type of material, and certain materials that you use emit light, and other ones don't. And also they
But
emit.
why do certain ones emit light and other ones don't?
Good question. So depending on their atomic structure. So this is a silicon, but depending on what you're doping it with, So remember how I was talking about the orbitals having specific energy levels? Depending on the material you have, the size of the separation between the energy levels is different. And sometimes you get a really large separation, and sometimes you get a tiny one. And what that corresponds to is the type of energy that's getting thrown out. So that's why we have like red LEDs, green LEDs, and blue LEDs. So do you guys know what type of color is the lowest in terms of energy, and what color is the highest in terms of energy?
Red is the lowest.
Red's lowest. What's the highest? Blue's the highest, right? Or violet. What happens after that? Ultraviolet. What happens before red? Infrared, right? So depending on the size of this band gap or this energy gap that you have, the energy that's being emitted sometimes is not visible to the human eye, or sometimes because it's infrared or it's ultraviolet, and we can't see in those ranges of wavelengths in terms of wavelengths.
So that's what those have?
Yeah, I would say so. I'm not actually 100% sure, but I'm pretty sure they all get excited and some don't. But they obviously emit radiation of some sort. And I think normal diodes, they're just emitting radiation that's so low energy that it's not even infrared and it's not anything, and it's just infrared. Yes?
So if I have a battery connected to a diode, like a 3-volt battery, and I get 30 milliamps through my diode, and if I put a 6-volt across, I should get 60 milliamps, right?
No. That's not, but you guys all had questions. I'll get to that later.
So in those diodes, like the normal ones, you said basically you just stope the two ends with like N-type and P-type, right? So like basically what it does is that it creates like a positive end and a negative end.
That's why it's polarized, right? That's why it matters which way you connect the diode.
Yeah, but like in that diode, just like it's sitting there right now, what's preventing the positive and the negative to like neutralize itself? So
that's a really good question. So actually, when you have it sitting there, you actually already have a tiny depletion zone. So obviously, when you don't have it hooked up to anything, they naturally want to come together in the middle. But once they form the tiniest slither of the depletion zone, they can't come in anymore. Right? You know how I was drawing your array of silicon atoms, and I had a bunch of dopants in them.
Right.
So imagine that, but like really big. So imagine I had positive doped silicon over here on this board. This whole board is positive doped silicon, and then over here I have my negatively doped silicon, and in the middle I have normal silicon. So remember how I said the way charge moves through semiconductors, they move by jumping into holes or jumping into electrons and shifting, right? But you just have normal silicon down the middle, or neutral silicon or semiconductor down the middle, so they don't have spaces to shift. So once that depletion zone is thick enough, thick enough for it to stop any charges from further neutralizing, it stops neutralizing and it stays positive on one side and negative on the other side.
Okay.
Shaw, you had a question?
Two questions. One of them, based on this, then when you put the charge through it, why does the depletion zone go away?
One. So we went through this example, right? So first, so you apply a big enough potential difference across the diode that it forces the force of repulsion from the terminals of the diode overcomes the depletion zone, and it pushes it physically pushes the positive charges or the negative charges into the opposite direction. And once that happens, they start forming the charges. They just flow through because the depletion zone is not there anymore, because you got positive atoms, you got positive charges, and you got negative charges flowing through.